everybody, my name is Olivia. I'm a graduate student at Washington State University, and I'm here today to talk to you and demonstrate this Venturi meter low-cost desktop learning module. Today we're going to do some experiments that'll show you the pressure trends as the water moves through the Venturi meter and the diameter changes, and we're also going to talk about how velocity changes as the diameter changes in this Venturi meter. If you haven't taken the pretest on Qualtrics yet, you can follow the link on your screen below. Please go do that before you continue watching this video. So I'll start today by talking a little bit about the setup for this Venturi meter. So we have a beaker full of water here, and the beaker has a pump in it. When I turn this pump on, water is going to move from the entrance of the Venturi meter here to the exit of the Venturi meter here. You might be able to see that the entrance of the Venturi meter has a larger diameter, and about at the middle of the Venturi meter, we call this the throat of the Venturi meter, the diameter becomes very small, and then it slowly expands again until it gets to the exit. We have 5 manometer standpipes here in the Venturi meter, and when I turn the pump on, water will be in these standpipes, and the height of that water is going to correspond to the pressure at that point in the Venturi meter. First thing I'd like you to do today, if you're following along with the Venturi meter worksheet, on page 1 there's 2 graphs, and if you could predict what you think the velocity trend and the pressure trend is going to look like in this Venturi meter as water moves from the entrance to the exit. Go ahead and do that now. Now that we've predicted what the velocity and pressure trends are going to look like, the next thing I'm going to do is turn on this pump. And when I turn the pump on, you should see blue water fill up the Venturi meter, and you should see different heights in these standpipes. Now. Okay, so you can see now that we've gotten all the bubbles out of the standpipes, our highest pressure is at the inlet of the Venturi when our diameter of the pipe is large, and as the diameter decreases towards the throat, we see a non-linear decrease in the pressure. Our pressure is lowest at the throat of the Venturi when we have the smallest diameter, and then as the diameter expands to the exit of the Venturi, our pressure goes back up. You can also see that the pressure doesn't recover completely by the exit of the Venturi, and that's actually because of frictional losses in the pipe. And so as the fluid moves through the Venturi meter, it loses energy due to friction, and so we have, even though the diameters are identical at the entrance and the exit, we have a lower pressure at the exit than we do at the entrance for the Venturi meter. The next thing I want you to do, if you're following along with the worksheet, on page 2 there's a graph at the top of the page, and I want you to plot the pressure trend through the Venturi meter based on what you see here on that graph. I'd also like to talk about velocity through the Venturi meter. Velocity is not very easy to see in this setup, but we have a video on our website. There's a link at the bottom of your screen. It's called Visualization of Flow Through the Throat. And I want you to go watch that video, and that will show you beads moving from the entrance of the Venturi meter through the throat, and you should be able to see the change in velocity of the beads as they move through the Venturi meter. And you can use that video to make a plot on page 3 of your worksheet of what you think the velocity looks like as the beads move through the Venturi meter. So in the video you just watched, you should have seen that the velocity speeds up as it goes to the throat of the Venturi meter, and then slows back down as it goes to the exit. We can think about this based on the continuity equation. So the continuity equation tells us that the mass flow rate of fluid through the Venturi meter has to be constant. Mass in equals mass out. And so we can use that to explain the relationship between area of a pipe and velocity. So as the area of a pipe decreases, or the diameter decreases, we have to have an increase in velocity to balance both sides of the continuity equation. Since the entrance and the exit of the Venturi meter have identical diameters, that means that the velocity at those points will be identical, even though the pressures aren't the same. The next thing we're going to do today is fill out the table on page 3 of your worksheet in question 8. And the data we're going to collect here is volume data, time data, and the height of the water in each of the standpipes for a bunch of different valve settings in this Venturi meter. What those measurements are going to allow you to do is to calculate the volumetric flow rate through the Venturi meter and also the pressure drop. Okay, so I'm going to go ahead and turn the pump on. This setting right here is going to be the fully open valve setting in your worksheet table. And so what we're going to do, when the water reaches the exit and starts flowing into this outlet beaker, I'm going to start my cell phone timer, and we're going to use this to measure the volume that's moved through the Venturi meter. And then we're also going to mark the heights of each of the manometers filled with water, and then measure those. And I'm going to turn my pump on and start my stopwatch. we're going to try to get some of the bubbles out of these tubes so we can measure them accurately. And we're going to mark the heights of the water in all the standpipes so that we can go back and measure them later. Our inlet feeder is almost empty, so I'm going to turn off my pump and stop my stopwatch. Okay, so the first thing we'll do is measure the volume of water that's gone through the Venturi meter, and it looks like we have 550 milliliters, and our time that we ran the Venturi meter was 42.64 seconds. Next thing we're going to do is measure the height of the water that was in all of the standpipes. And so I have a ruler here. We're going to measure from the center of the tube up to where I marked the water height. Our first manometer height is 12 centimeters. Manometer number 2, we have 11.7 centimeters. Manometer number 3, we have 6.5 centimeters. Manometer number 4, we had 9 centimeters, and manometer number 5, we had 9.5 centimeters. So you go ahead and fill in all that data on the fully open valve setting of the loop. Okay, so we're going to redo this, and I have closed the valve slightly further, which is going to slow down the flow rate through the Venturi meter. We're going to do the same thing we did last time. I'm going to start my pump, turn on my stopwatch, and then we're going to run this through, measure the water heights, and then measure volume and time at the end. Okay, so turning on my pump. So you can see that the pressure overall is much lower this time because the flow rate's so much slower. I'm going to go ahead and mark the water height in the tubes. I'm going to let this run for just a little bit longer until our inlet beaker is more empty. And I will stop my pump and stop the stopwatch. Okay, so our water volume for this run was 325 milliliters. And our time was 54.33 seconds. And the last thing we're going to do is measure the manometer heights again. For manometer 1, we have a height this time of 3.3 centimeters. Manometer 2, we have 3 centimeters. Manometer 3, we have 1.7 centimeters. Manometer 4, we have 2.4 centimeters. And manometer 5, we have 2.5 centimeters. You can go ahead and put that data on partially closed position 1 on your worksheet. So we're going to do this one more time. Slightly increased the valve and flow rate this time, so the water will be moving faster and our manometer height should be higher overall. That looks pretty good. So I'll go ahead and mark the water heights. This run for a few more seconds. And we'll go ahead and stop our pump and stopwatch. Okay, water volume for this trial is 525 milliliters. And our time is 47.67 seconds. And we're going to measure the water heights now. Manometer 1, we have 9 centimeters. Manometer 2, we had 8.8 centimeters. Manometer 3, we had 4.7 centimeters. Manometer 4, 6.9 centimeters. And manometer 5, 7 centimeters. So that's all the data we're going to collect today, and you can use this data to do the homework portion of your worksheet and some calculations if your instructor has told you to do that. Thanks for listening today. I hope you learned something new about Venturi meters and the relationship between diameter, pressure, and velocity. Bye!